So today I'm going to present NeuroMap. So maybe some of you were here on Wednesday when Justine did this amazing lecture where she allowed you guys to actually try the toolbox. Today I won't let you do that for the sake of time, but basically I'm going to present some of its main things, and I'm also going to show like an application of NeuroMaps like to some in a specific context, which is the field I'm working in right now, which is network neuroscience. So basically, NeuroMaps in general is a tool for contextualizing human brain maps, and what do we mean by that? Oh, and actually, by the way, okay, that's a very important point. So I did a presentation today, Justine did it on Wednesday, but actually none of us actually developed this toolbox. The actual creator of the toolbox is not here. His name is Ross Markello. He was an amazing PhD student. Now he's in industry, and now we took over like this toolbox, and we're maintaining it, and we're answering all of your guys' questions. But the real developer, like the real guy behind NeuroMaps, is actually Ross Markello. So like you might want to thank him if you see him in the street somewhere, because he's an amazing guy. But yeah, so let's go back to the actual presentation. So contextualizing human brain maps. What do we mean by that? Well, basically, it's oftentimes we have like a brain map in our studies, for example, here, cortical thinning, and we want to know like what's happening with this brain map. We want to understand like whether it's enriched, for example, in specific biological entities or processes. So for example, we want to know if like the cortical thinning in a specific region is related to some gene expression happening there. Is there specific genes that cause this cortical thinning? Is there specific neurotransmitter receptors or like metabolic processes happening in these specific regions? And to do that, we need a toolbox, and this is what NeuroMaps give you. It basically meant to do statistical comparisons between brain maps, right? It's available on GitHub and also on like the Python package index, and it's also available as a Docker container for those of you that don't want to install all the dependencies, which are very minimal. It's basically all you need is the connectome workbench and some very basic Python modules. And by the way, I invite you guys to check the documentation if you want to know more about the actual functions of the toolbox. And I'm going to just briefly go over like some of the main functionalities. The main one is perhaps the transformations that we've created to be able to compare brain maps that are usually defined in different spaces. So for example, if we have a map in MNI 152 space, so volumetric data, we'll want to compare this map to other brain maps that are in different coordinate systems. So for example, you'll have cortical thickness T1, T2 in FS-cellular surface if you use, for example, the human connectome project data. Otherwise, you might have like a PC1, so the main axis of gene expression in the brain that you will have acquired from the Allen Institute, and then this is going to be an FS average surface. And you'll also have other studies that have published their data in civet surface, for example. And these are all different, so you need transformations to do that, to be able to compare them efficiently. And this is what we provide here. We basically provide mappings from volume to all of these different surfaces using registration fusion framework, and we also provide mapping between all of these different surfaces using multimodal surface matching. We also, and this is actually an example of how the code would look like, so it's basically one simple line of code. So basically, for example, if we want to transform between MNI 152 to FS average, this is going to be one line, and this is actually the name of the function. So it's not too hard and too complicated, and you give your MNI brain map, and then you specify the density you want for your FS average, and you get your brain map, as simple as that. You can also use resampling, which is actually not like, it's not just like linear resampling, it's actually like doing the transformation that you want, and you specify like your source map, your target map, you specify the spaces they're in, and then you just say transform this map to my target. So then you have two brain maps that end up being in the exact same space, and then you can actually do some comparison. It's very simple. And then we also have the data sets, right? Because we give access to a bunch of different brain maps from microstructure, metabolism, function, electrophysiology, expansion, so evolutionary and developmental, and also like genomics, so gene expression. We have also, perhaps the most interesting one is this one that Justine and a lot of collaborators helped her generate. So this is basically a PET tracer density maps for 19 different neurotransmitter systems, which basically tell you like the density of different neurotransmitters across the cortex. This actually is a good way here, like I just want to point out that this is a very important thing about NeuroMaps is we don't acquire any data here. We're just collecting data from a bunch of people, some of whom are actually in the room right now. So it's important that when you use Neuromap, you actually cite the actual original authors of the papers and not just us, because we didn't do much, honestly. Yeah, so this is an example of how to do it. So like you literally just import like the datasets module, and you say datasets.fetch annotation. You can fetch all of them if you want. There's actually 78 brain maps at the moment, as we saw with Justine on Wednesday. And you can specify some things if you don't want all of them. So you can say tags equal receptors, so you'll just get the receptor brain maps that are shown here. And then the important thing about neuromaps is we also provide spatial nulls, because the idea is that when we do, after we do the transformation and we compare it to our original source map to all of these different target maps, we'll want to contextualize them, and we do that sometimes by doing correlations between all of them, right? So like we get a bunch of Pearson's correlation, and the important question, as always, is like, how do we evaluate the significance of these correlations, right? This might seem easy, but it's actually not, because most of the brain maps in the brain are spatially autocorrelated. Sometimes it's just because like we do some smoothing, some transformation, and it's also because it's a very, very basic feature of the human brain, right? Every single brain map you'll have is going to be spatially autocorrelated in some way. And you might wonder, okay, what's the point? Or like, why does it matter? Well, because when you do statistical analysis, if you have two completely random brain map, no spatial autocorrelation, the odds are you'll have no correlation, right? But if we take this exact brain map and we increase the smoothing of that brain map, well, you'll end up with some some actual correlations, even though those are completely unrelated. And this is actually not just like, I didn't just pick some random example, because this is actually a fact about spatial autocorrelation, which is that when you increase the spatial autocorrelation of brain maps and we compare them together at random, what's going to happen to the distribution of correlations, of random correlations we get, is that it gets flattened out and it's getting more wide. And so when we evaluate the p-value of a correlation, we have to take that into consideration, because if we don't, we can look on the right here, and this is basically representing the false discovery rate of our experiment, and we see that while we usually want a false discovery rate of about 0.05, right, and the actual p-value, we see that with spatial autocorrelation in our data, we almost get 100% of false discovery rate, even though there's actually nothing here. So this is quite problematic. So we actually need to handle that if we want to do actual inference based on our data. So what we do here is permutation testing, basically what we suggest actually people doing. So for those of you who are not familiar with this type of statistical test, the idea is that you have two brain maps. You first get a correlation, the empirical one, and then what you do is you generate a bunch of null brain maps. And then what you do is you take the source brain maps, which is an X here, and you correlate it with all of the Y nulls that I'm showing here, and we get a distribution, a null distribution of correlation scores. And then what we do is we count the number of null correlations that are greater than our actual empirical one, and then we normalize it, and then we get a p-value out of it, which tell us if our results are significantly significant based on the spatial autocorrelation of our brain maps. And the important thing is that we have to generate brain maps that preserve some important feature that we want to control for. In this case, it's the spatial autocorrelation. So the whole idea here is that we generate brain maps that are still spatially autocorrelated in the same way as our source data. So we're going to do that by doing either spatial permutation models. So these are the classic spin tests, where we take a brain map on the surface, we project it to a sphere, we rotate it, and then project it back to the actual brain. There's another way to do it when we don't have surface data, which are going to be parameterized data models. So in this case, we will basically just generate new brain maps that have the same spatial autocorrelation as our empirical one. And you might wonder, and this is actually an example of how you do it with our toolbox. Again, one line of code, so nulls, and then we call the type of null. So we have a bunch, as you see here. All the names that you see are actually different nulls that exist in our toolbox, and then you say nulls at Alexander block, which is actually not here, which is funny because it's the only one that's not named above, but it's another option here. And then you say surface map, so your surface map, because it's a spin test in this case, you specify the atlas and the density of your brain map, and there you go, you specify the number of permutations you want. And does it work? Is it worth it, right? Because I'm showing here that there's a lot of false discovery rate when you have high spatial autocorrelation. I keep saying like false discovery rate, but I always mean like a false positive since the beginning. Sorry about that. So yeah, so what we see is that the false positive rates actually drastically decrease with spatial autocorrelation preserving nulls for most of them. And actually what we can actually point out very quickly is that parameterized nulls are slightly less statistically accurate than spatial permutation nulls, but like they're still pretty good and very much better than spatially naive null models. And that's about it. And then you can actually see that if you actually use those null models, like most of the correlation that would be significant if you don't control for it are not anymore. And like you can actually identify actual important significant relationships between your brain map and the brain maps that exist in the literature. So in this case, this would be like allometric scaling for schizophrenia cortical thickness thinning. So yeah, that's about it. Because for the sake of time, I won't show you that. But like one of the cool applications of neural maps and in brain maps in general is to do some new research, right? Obviously, not just like doing some random comparison. And in our case, what we like to do is annotated connectomics. So we basically take a connectome, and we add on top of it all of these different brain maps that we've acquired over time. And this allows us to ask a bunch of new questions from graph theory. I think, yeah, a lot of new questions, for example, like graph theory metrics like hubs and communities and path and motifs. Those are all concepts that have existed for a long time, but we've never considered them in context of like brain maps and annotations. And this allows you to do that, like a tool like neuromaps. And this also allows you to, by taking regional heterogeneity into account, it actually allows you to create like better network models of the brain. And that's also really great. And so yeah, that's about it. And it's very simple to install, pip install neuromaps. So also available as a Docker container. And feel free to like ask us a bunch of questions if you have, and like tell us if you find bugs and everything. And please contribute if you have any ideas. And yeah, here's the QR code for the documentation. And a big thank to Justine and Ross. We are the main guys behind that. And Zhengxi as well. I want to point out Zhengxi there as well because he's very important for that work, and he's done a lot, and he's not here, unfortunately, but I don't want to forget him. So yeah, that's about it. Is there any question?
Thank you very much also for staying in time. And there would be time for exactly one short question again. Yeah, please, to the microphone. Hurry.
Great. So thank you very much, and I think it's a wonderful toolbox. And this is maybe a bit of a different question, but like your documentation is super great, right? You have like one code basically, and you get your results. Is there also like a risk of that, like that many people will be able to use it that don't quite understand what they're doing? And do you have any kind of like anecdotal experience with this and ways to prevent that people just plug and play and go from there?
Great question, because it's like, I mean, it's the kind of thing that when you give tools that are easy to use, some people like don't read about the actual techniques. We've never thought of like constraining people, and so that like, yeah, I don't know what they're gonna do with it. We hope they don't do that, but yeah, there's no measure in place to prevent them from just using them. But we do encourage a lot people to actually read about the techniques, because they're not like, I mean, yeah, exactly, this one line of code, but they're not straightforward. And I had a demo, which I didn't present, but like I was showing like some very particular thing to keep in mind. We're actually always like trying to update our methodology and documentation to make sure they're all there, but sometimes we don't have control over that, unfortunately, yeah.